When we talk about capacitors, the most common capacitor that we encounter in our studies is the parallel plate capacitor because it is the simplest to understand. So a parallel plate capacitor is simply two sheets of material, of conducting material. So we have two sheets of material separated by some distance. And initially, we will assume that this capacitor is not charged, which means that there is no imbalance of charge between these plates. There is no excess charge on either of the plates of this capacitor. Now, if I were to connect this capacitor with a source of electrical energy, let's say that I connect this capacitor with a cell. So here is my cell. So this is the positive terminal, this is the negative terminal. We will now notice that because of this source of electrical energy, charges will start to move towards the plates of these capacitors. Now, initially, we have assumed that the capacitor is not connected to anything, there is no excess charge on it, which means that while the potential of the external source will be capital V, the potential inside these plates or the potential between these plates at the beginning is 0. Let's say that we are moving a tiny amount of charge, a vanishingly small amount of charge that we can call dq. So dq is an infinitesimally small amount of charge which is moving from the positive end of this cell or battery and it is traveling into this capacitor. So here it is traveling into this capacitor. So here we have a tiny positive charge, that is dq. Since the capacitor had no potential between the plates initially, there is no excess charge already existing on that plate. So there is no repulsive forces. So the infinitesimal amount of charge that has traveled here did not meet with any opposition. There was no resistance to its movement. So no work has been done in moving this tiny amount of charge into this capacitor. However, now that this tiny amount of charge dq exists on this capacitor and in response, we also have a tiny negative charge on the other side of this capacitor to maintain charge neutrality, we realize that if the power source, that is the battery, tries to send more charges into the positive plate, into the upper plate, they will encounter the repulsive force of the positive charge already existing on this plate, which means that while the first infinitesimal amount of charge dq could be put on this plate without any work being done, any further charge transfer to this plate will have to deal with the opposition of the charge already existing on that plate. So work will have to be done in order to move more charge into this plate. And as we keep on adding charges into this plate, the potential between the plates will also increase. So we can denote the potential between the plates as small v. And we can keep on doing this, we can keep on increasing the potential of this capacitor, the potential between the plates, until the potential of the capacitor plates becomes equal to the potential of the external energy source, at which point there will be no further movement of charges between the capacitor and the battery, because both of them have reached the same potential. The difference in potential is now 0. So the work done in moving this amount of charge, this tiny charge dq, and in response to that we get a tiny potential difference v, that will be equal to delta w, that is the small amount of work done in this process, is equal to small v times dq. So this tells us that in order to move a tiny charge dq, we have done some work and that work is now stored between the plates of this capacitor, you could say, in the form of a small electrical potential, that is small v. Now, every subsequent packet of charge, all the charges that follow this first packet also have to face the opposition of the charge already existing on that plate. So work has to be done in pumping more charge onto this plate. So we can say that if we were to integrate, so we can write this as dw. So if delta becomes very, very small, we can call it d. So dw is equal to vdq. And if we want to know the total amount of work done in moving these charges onto these plates, we can say that that is the integral of dw, which is equal to the integral of v dq. So we can write this equation as w is equal to the integral of v becomes q upon c. So this is q divided by c dq. If you integrate this expression, we get the following expression. W is equal to q square divided by c times half plus a constant of integration. So let's just call this k1. Why does this exist? The reason that we have a constant of integration is that this is not a definite integral. We have not defined the limits for this integral. Physically, what this means is we do not know that if there was any charge already existing on this capacitor before we started this experiment. For the sake of simplicity, we are going to assume that, as we said earlier, there were no excess charges on this capacitor when we began the experiment, which means that this term becomes equal to 0. So we can say that W, that is the work done on this capacitor, is equal to half Q square divided by C. Now remember what I had said earlier. I had said that the transfer of charges between the potential source, that is the battery, and the capacitor will keep on taking place until both of them have reached the same potential. So here we have the result, W is equal to half Q square upon C. Since we know that Q is equal to CV square, the point at which the capacitor will no longer be charged further is the point where the voltage small v between the capacitor plates becomes equal to capital V, that is the potential of the source. So in that case, we can say the work done in making the potential of the capacitor reach the same value as the external voltage source, W will be equal to half multiplied by CV, that is capital V, the voltage of the external source, whole square divided by C. If you simplify this, we get half CV square. And this is the final expression that we require for a parallel plate capacitor.
Manorama Horizon. Learning made simple.